All right, so this is section 2.4 of Math 146. We're going to be talking about the properties and graphs of rational functions. And what I will preface this by saying is that this is really going to be important as to your knowledge of how fractions work. Because rational functions are simply fractions, polynomials over polynomials. A lot of the stuff that we're going to be dealing with is very important that you understand how fractions work. And hopefully this will make sense as we go through it. All right, so what I'm going to try and do here in the beginning is we're just going to go through the different things that we're really going to need to know. Now, there are much more involved ways and more detailed ways of doing what we're going to be doing, but this is really going to be coming down to, can we get the appropriate information and can we make a sketch of the rational function based upon the information that we are given or that we can find? Again, there are much more advanced ways of doing this, which hopefully you will get into when you get into calculus, but understanding this will go a long way into helping that. Okay, so when we are talking about rational functions, we are going to need to find a bunch of different things. We are going to need to find all of the asymptotes. And in this case, there are actually going to be three types of asymptotes that you can have. So asymptotes. There are three types. You can have a vertical asymptote, which has its own properties. You can have a horizontal asymptote, and then you can have what is called an oblique, or some people call it slant asymptotes. I've actually grown up knowing them as slant asymptotes as opposed to oblique, but they are pretty much the same. Well, they mean the same thing. All right, so vertical. The one thing about asymptotes is they are, in this case, all linear. Okay, these are all going to be lines in some case. So it should make sense that you can either have a vertical line straight up and down, a horizontal line left and right, or something which is neither, which is slanted, has some kind of a slope to it other than a vertical or horizontal slope to it. So how do we find these things? So a vertical asymptote in its simplest form is any value that makes the denominator zero, but not the numerator. So if I can take a specific value for x, plug it into the denominator, and it makes the denominator 0, but it does not make the numerator 0, that would be the location, or excuse me, that would be the location of the vertical asymptote, and you could write the equation for it, which we will do. Horizontal asymptotes. This is really what is known as end behavior. End behavior, or basically what is happening as the graph goes way off to the right and way off to the left. If you think of your standard XY graph, that is what is called the end behavior. So what is the function doing, or what is the graph doing as the graph goes way off to the right or way off to the left? Or basically as we let x go further and further towards infinity or further and further towards negative infinity. And there are, again, fractional ways for us to look at this. So there's really three different things you are looking for. Remember that these are going to be rational functions, so it's a polynomial over a polynomial. So each polynomial, the numerator and denominator, are going to have degrees associated with them. If, and this is the first one, if the degree, I'm going to call that capital D, no, let's not do that. Let's just say the DEG. If the degree of the numerator is greater than the degree of the denominator. So think about something like if you had an x cubed plus a whole bunch of stuff, and then an x squared in the denominator and a whole bunch of stuff, or an x, excuse me, in the denominator. This is going to make more sense when I actually write it out. But basically think about it like this. If what you have in the numerator is larger than what you have in the denominator, and they keep getting larger, then ultimately your fraction keeps getting larger. And if the fraction keeps getting bigger, the overall number gets bigger, which means that you really aren't going to approach any specific type of a value. So in this case, there would be no horizontal asymptote, because the graph is just going to keep on getting bigger and bigger and bigger, or if it's negative, it's going to keep on technically getting smaller and smaller and smaller. It will not approach any specific values. 2, we could flip those. We can say that the degree of the numerator is less than the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, meaning that the degree of the denominator is bigger, that means you have a bigger bottom to your fraction. And a bigger bottom to the fraction ultimately means that the bottom gets bigger and bigger and bigger while the top remains relatively small comparatively. Well, a huge denominator over a tiny little numerator basically is going to get really, really, really close to 0. So your horizontal asymptote would be the x-axis, or the equation y equals 0. And then you have the case where the degree of the numerator equals the degree of the denominator. If this happens, the growth rate of both the numerator and the denominator, as these numbers get really big for x values, is going to basically be the same. So what you do is you actually divide the leading coefficients. So it would be y equals, and then whatever the leading coefficient of the numerator is, divided by the leading coefficient of the denominator. So we'll say the leading coefficient of the numerator divided by the leading coefficient of the denominator. And again, remember, this is going to be just kind of a shorthand of how we do all this stuff. When we start doing the examples, this should make more sense. And there is a very good chance this will be a multi-video lesson, just because of the fact that these problems can take some time. All right, and then the last thing that we have is a slant asymptote, or an oblique asymptote. And the only way for you to get an oblique asymptote is for the degree of the numerator to be exactly 1 more than the degree of the denominator. For example, if you were to have something, like I said before, if you had something where x cubed was the highest power on top and you had x squared in the denominator, then instead of having a horizontal asymptote from that, you would actually have a slant asymptote. And hopefully you'll see why that is when we actually go through an example. All right, so that's the first set of things that you're going to think about. Well, not necessarily the first, but one of the sets of things you're going to think about are the asymptotes. And in general, I'm not going to write this down specifically, horizontal and slant asymptotes can be, we call it compromised. They can actually have values where the graph goes up and down through the horizontal and slant asymptotes until you get far enough out on your function, and that's kind of up to interpretation, but until you get far enough out that the values are starting to approach the asymptotes, then they won't compromise them, then they won't cross them. But towards the interior, it's okay. Vertical asymptotes are different. Vertical asymptotes technically cannot be compromised. They cannot be crossed through. Okay, there are examples where a function might actually hit a vertical asymptote, but it will stop. It won't go through it. But that's a completely different type of function. That's not a rational function. For rational functions, vertical asymptotes cannot be touched. All right, so you're going to find the asymptotes. We also need to make sure that we know how to find a hole in the graph. And a hole in the graph is actually one of the easier things to find. It is any value that makes the numerator and denominator equal to 0. So if you can plug a value in for x and it makes both the numerator and the denominator equal to 0, then that value of x is the location of a hole. So technically a hole is a point. It's just a point that doesn't exist on the graph. We'll over-exaggerate that point when we actually sketch the graphs. But since it is a point that technically doesn't exist, where the hole is actually going to be given as an ordered pair. So that's a hole. So those things all kind of go together. All right, we also need to be able to determine domain and range. And domain is the set of all of the x values. So basically what you're looking for here, because it's going to be too hard for us to write out every single point individually, we're going to write out intervals for your domain. And what you're looking for is you want to set the denominator equal to 0, and whatever makes the denominator 0 has to be eliminated from your domain. Everything else should be fine. So you'll set the denominator equal to 0 and eliminate those values. And we'll show how to write the domain after that. The range is slightly easier. Because the range is the set of all the y values. Actually, I don't want to say it's slightly easier. It's the set of all the y values or dependent variable values. In this case, you're going to have to do a little bit of analysis once you maybe either see your function graphed or figure out what's going on with it. We'll talk more about the domain, about the range when we get to it. We are also going to, in order to be able to graph these things, we're going to have to find the intercepts, the x and the y intercepts. So x and y intercepts. Okay, these aren't as difficult to do, but you still have to do some work. The x-intercepts are going to be whatever makes the fraction equal to 0, which means you're going to set your numerator, equal to 0. Whatever values those give you are going to be your x-intercepts, as long as it doesn't also make the denominator 0, because if that's the case, then it would be a hole instead of an x-intercept. So you'll set the numerator equal to 0. Just make sure it doesn't make the denominator 0. The y-intercept is probably the easiest of all of them. The y-intercept is simply plugging in 0 for x. And because these are going to be functions, you will only ever have one y-intercept, whereas obviously you could have multiple x-intercepts in a function. Can't have more than one y-intercept because then it would fail the vertical line test. All right, so those are the basic categories that we're going to use in order to find and sketch these graphs. We're also going to use a little bit of analysis based upon the information that I gave you, but those are the main things. So let's do probably one example on this video, and then we'll come back with another example in a second video. All right, so here we go, example 1. So we're going to have f of x is equal to x divided by quantity x minus 1 times the quantity x plus 2. All right, so we got a bunch of things to figure out. Again, it doesn't have to go in the specific order that I gave them to you in. You can do it in any order that you want to, whatever makes the most sense to you. Nice thing is the denominator here has been factored. This is not going to be an incredibly difficult one in order to find values, but it is something that we're going to look at. So we could find our asymptotes first. So the easiest thing typically once it's in its factored form, which this is to find your vertical asymptotes. So we have a vertical asymptote where whatever makes the value of the denominator 0, as long as it doesn't make the numerator 0. So you should be able to look at this one quite easily and say, well, if I plug in x equals 1 or x equals -2, both of those are going to make the denominator 0. And of course, neither -1 or -2, if you plug that in the numerator, makes the top 0. So I've got vertical asymptotes at x equals 1 and x equals -2. And because these are lines, you need to write them as equations of lines. It's just not, you don't just write down 1 and -2. You write x equals 1, x equals -2. Those are vertical lines, vertical asymptotes. Okay, now let's look and see, do we have any horizontal asymptotes or slant asymptotes? And you will either only have one or the other. You cannot have both. Okay, if you have a slant asymptote because the numerator would have a higher degree than the denominator, you won't have a horizontal, and vice versa. Okay, so if we look at this, the degree of the denominator is technically 2, because if you were to distribute everything out, you'd have an x squared as your highest power term. The degree of the numerator is 1. So since the degree of the denominator is greater than the degree of the numerator, your horizontal asymptote is going to be y equals 0. Okay, again, if the degree of the denominator is bigger than the degree of the numerator, for rational functions, this will always be the case. You'll have y equals 0 as a horizontal, which means that you have no slant asymptotes. And nothing made both the numerator and the denominator 0 at the same time, so we have no holes. Okay, and it's good to state that. All right, we need to find the x and the y intercepts. I am going slightly out of order from what I did before. So the x-intercept is whatever makes the numerator 0. Well, in this case, the numerator is just x. So if you set x equal to 0, then simply x equals 0 is your x-intercept. And as it turns out, if x is 0, then y is also 0. So that would be the x-intercept, the point 0, 0. The y-intercept is what you get when you plug in 0 for x. Well, that just happens to also be 0, 0. Because if you plug 0 in for x, you get 0 over some number which is not 0, which is 0 as a fraction. So there is your y-intercept. So it looks like this thing hits the origin for both the x and the y-intercept. And then the last thing we have to talk about is domain and range. So domain, the easiest way to look at domain is to figure out, okay, in this case, my vertical asymptotes are x equals 1 and x equals -2. Those are the only two values that make the denominator 0. So those are the two values that can't be included in our function. So your domain is going to be everything except for 1 and -2. So the way you write that in intervals is -∞, and then you go to the first numerical value, which would be -2 from left to right on a number line. That's going to be in union with, then I'll go from -2 up to 1, and then we're going to go from 1 off to infinity, because we can include every other possible number other than -2 and 1. So -2 and 1 is pretty much your starting and your stopping point on your interval. Now the range, we might have to do a little bit of thinking here. As a matter of fact, it probably is going to be a good idea for us to sketch this, and then we'll talk a little bit about the range. There are ways to figure this thing out otherwise, but I think we should do the sketch first, and then we'll come back to the idea of the range. So let's go ahead and draw just a basic XY plane. This will not be extremely detailed, but we're going to detail it enough that gives us the information we need. Okay, so you want to start off probably by sketching your vertical and your horizontal asymptotes. So I have a vertical asymptote at x equals 1. We'll say that this is x equals 1, and the way we draw that is a dashed line. We'll say that that's 1. We have one at x equals -2. So if that's 1, then that's -2. So we have a vertical line there. That's at -2. We have a horizontal asymptote at y equals 0, which is the x-axis. When it's on the axis, it's a little bit more challenging to draw just because you're drawing usually right over top the axis. In my case, because it's green, it might be a little easier to see. But you'll do a dashed line there at y equals 0. Don't have any slants or any holes to worry about. So now we have to figure out what is this graph doing around these asymptotes. So this is where you're going to have to use a little bit of logic, and then we're going to do a little bit of evaluation as well. So I've basically got three different sections to worry about. I've got the section which is to the left of my -2 vertical asymptote. I've got in between the -2 and the 1, and then I've got from 1 off to the right. So you're looking at kind of your domain. You've got three sections to worry about: here, here, and here. What is happening with my graph? Doesn't really matter where we start. Let's start to the far right because we'll deal with the positive numbers the best that we can. So if you were to take a value like +2, because I know that that is in the section to the far right, and you were to plug in a +2 into f of x, one thing I really care about here is the value going to be positive or is it going to be negative when I plug in +2? Granted, it's probably more accurate to go ahead and get the actual value, but if we're just doing a sketch, it really just makes sense for us to analyze this. So let's look at this. If we were to plug in +2 into the top, obviously we get +2. If we were to plug +2 into the denominator, I've got two different pieces to plug it into. I've got the x minus 1 and the x plus 2. If I plug a 2 into x minus 1, yes, I can get the value. I'm not worried about that as much, but it would be positive, right? 2 minus 1 is positive. Then if you plug +2 into x plus 2, 2 plus 2 is also positive. So every value that I get by plugging 2 in is going to create a positive. Technically, it would be a positive over two positives multiplied together. So it would give me a positive value. So if I take if I take x equals 2, everything I have for that part of the graph is going to be up in here somewhere. It's going to be all positive. So I know that the graph exists up there. It cannot exist below because that would produce negative values. And how do I know that this thing can never drop below that horizontal asymptote and give me something negative? Well, in order for it to do that, it would actually have had to have crossed through the x-axis someplace. But I have no other x-intercepts other than at 0, 0. So I do know that everything has to exist in that kind of that upper right section. So if you actually plug the value of x equals 2 in here, we'll just create a little chart. This will be our x values. This will be our f of x values. If you plug in 2, you would get 2 over, that looks like that would create a 4 in the denominator. So 2 over 4 is 1/2. So you would get the point 2, 1/2. So 2, 1/2 might be something right around there. All right, so now let's see what happens. As this thing goes further and further off to the right, as my x values get bigger, again, this thing is going to approach y equals 0, so that we know it's going to do this and start to ride right along that asymptote. As the values get closer and closer now to the 1 going to the left, remember it's a vertical asymptote, so it can't go through it, it can't crash into it, so it only has one of two choices. It can either go up or it can go down, and it can ride along the vertical asymptote in that fashion. Well, in this case, we know that it has to go up. Again, the reason it can't possibly go down here is because it would have to cross through the x-axis again, and there's no other x-intercepts. So the only choice that this function has is to do that. Okay, so now we've sketched kind of that right-hand portion. Let's sketch the left-hand portion, and then we'll come back to the center. So we look at the left-hand portion. It's the same general idea. Pick a value which is to the left of -2, such as -3. If I plug the -3 into the top, fix that real quick. If I plug -3 into the top, I'd have a negative on the top. See, -3 minus 1 in the bottom is a negative number. -3 plus 2 is also a negative number. So I'd have a negative over a negative times a negative. So 3 negatives being multiplied or divided together will produce a negative value, which tells me all of my values will lie down here below the x-axis. And again, if we want the actual value of that, oops, got rid of my -3 somehow there. Then we would plug in -3 on top and bottom, see what we would get. So that would be -3 over, let's see, that's going to be -4 times -1, which is +4. So -3 over +4 would be -3/4. So we would be at the point -3, -3/4, someplace right around there. And again, remember, this is a sketch. It's good to have those values, and you can label the values later. So we know that as this thing goes off further and further to the left, it will approach the horizontal asymptote. And as it goes towards the right, as it approaches -2 asymptote, can't possibly go through it, can't go up because it would have to go through the x-axis again. We don't have any more x-intercepts, so it has to go down. All right, now let's take care of the center section. The one thing that we do know for sure about the center section is that's where our x and y intercept is. It just happens to be at 0, 0. And as you can see, that actually touches your horizontal asymptote. Again, in the middle of the function, it's okay. It's what happens as you go off, it's way off to the left and the right that it won't touch anymore. All right, so we kind of have to do a little bit of analysis. Either the function can do something where it stays on one side, either all positive or all negative values of the x-axis, or it can flip-flop and go from one to the other. So we just have to do basically a real quick sign analysis of what it's going to do. Let's pick a value in between 0 and 1. So something in this range right here for x, and see what it does. I only care what the sign is. That'll tell me the direction that this graph is going to go. So if we plug a 1/2 into the numerator, of course that's positive. If we plug a 1/2 into the denominator, 1/2 minus 1 is negative. 1/2 plus 2 is positive. So in the denominator, we're going to get a negative times a positive, which is negative. The numerator was positive, so we're going to get a positive over a negative, which is a negative value, which means that if I were to plug a 1/2 in, I'm not really going to find the value here. I just know that it's going to create a negative value. So as x goes towards that x equals 1 vertical asymptote, this thing has to go down. Okay, now let's see. Is it going to go down as we go to the left as well, or is this thing going to go up? Let's double check. Let's take a number in between -2 and 0, like -1. Plug a -1 on top. That's going to be a negative. Let's do it this way. It's going to create a negative on the top. If I put -1 into the denominator, that's going to be a negative times a positive. So we'll have a negative on the bottom, but dividing a negative by a negative is positive. So the overall thing here is going to be positive, which means it's going to be above the x-axis. So as we go towards the -2 asymptote, this one will stay up, and it will go in that direction. All right, that is just one of several possible examples of the way a graph could be sketched using the information given. Oh, and by the way, if you we didn't talk about it, but the range here, now that we see the graph, because of that middle section, or actually either one of the sections, it looks like every single possible value of y is taken on. So it looks like this will go from -infinity to positive infinity. So we can get any possible y value. Okay, that is plenty enough for this video. I'm going to try and find one example where we probably have a slant asymptote and even possibly a hole in the graph to see how you would graph those for the next video.